Picture this. It's 1932 in Helsinki, Finland. While American automakers are building massive four-stroke engines that weigh as much as small boats, a Finnish engineer named Kaarlo Tahko is working alone in a converted warehouse, designing an engine that violates everything Detroit considers sacred. His creation? A two-stroke V8 that produces 120 horsepower from just 200 cubic inches while weighing 40% less than Ford's flagship engine. In an era when Henry Ford's engineering philosophy dominates global automotive thinking, this unknown Finnish inventor is about to prove that sometimes the best innovations come from those willing to challenge orthodoxy. The automotive world of 1932 was experiencing a revolution. Ford had just released their flathead V8, the first mass-produced V8 engine affordable to average Americans. It was a marvel of production engineering, 221 cubic inches, producing 65 horsepower, cast in a single block for economical manufacturing. Every major automaker was either copying Ford's approach or scrambling to develop their own four-stroke V8s. The four-stroke cycle was gospel: intake, compression, power, exhaust. 4 distinct strokes, 2 crankshaft revolutions per power cycle. It was refined, proven, and universally accepted as the only serious option for automotive propulsion. But here's where it gets interesting. While Detroit's engineers debated camshaft placement and valve configurations within the confines of four-stroke design, Kaarlo Tahko was questioning the fundamental premise. Why did car engines need 4 strokes at all? Marine engines and industrial power plants had been using 2-stroke designs for decades. Every revolution produced power. No wasted motion. The power-to-weight ratio was theoretically superior. The problem was that automotive 2-strokes were notorious for being smoky, inefficient, and crude. They mixed oil with fuel for lubrication, creating blue smoke and fouled spark plugs. They couldn't control their breathing properly, wasting fuel out the exhaust port. Detroit had tried 2-stroke car engines in the teens and 20s. They all failed commercially. Tahko saw these failures not as proof that 2 strokes couldn't work in cars, but as evidence that nobody had engineered them properly for automotive use. His background was unique. He'd trained in marine engineering at the Helsinki Technical Institute, then worked on industrial diesel engines before turning his attention to automobiles. He understood 2-stroke theory at a level most automotive engineers never bothered to achieve. More importantly, he understood that the limitations everyone accepted as inherent to 2-stroke design were actually just engineering problems waiting to be solved. The warehouse where Tahko worked was a far cry from Ford's River Rouge complex. No assembly lines, no army of workers, just Tahko, 2 assistants, and a collection of machine tools he'd acquired from bankrupt factories during Finland's economic struggles. The building had been a textile mill, and Tahko kept the overhead line shafts to power his lathes and milling machines. In winter, the space was so cold that cutting oil would congeal, forcing them to preheat tools with blowtorches. These conditions would have been unthinkable at Ford or General Motors, but they forced Tahko to think differently about every aspect of his design. The core innovation of Tahko's engine was deceptively simple. Instead of using piston-controlled ports for both intake and exhaust like traditional 2-strokes, he used intake ports in the cylinder walls, but added proper poppet valves in the head for exhaust. This hybrid approach had been tried before in stationary engines, but never successfully adapted to the high speeds and variable loads of automotive use. The intake ports were positioned precisely 78 degrees from bottom dead center, uncovered by the piston, just as cylinder pressure dropped below atmospheric. The exhaust valves opened 95 degrees after top dead center, staying open just long enough to evacuate combustion gases without losing the incoming charge. Think about that timing for a second. In a conventional 2-stroke, the exhaust and intake ports open almost simultaneously, relying on gas velocity and pressure waves to hopefully push exhaust out while pulling fresh mixture in. It's chaotic, unpredictable, and wasteful. Tahko's design separated these events. The exhaust valves closed before the intake ports opened fully, creating a brief moment of depression that literally sucked fresh air through the ports. No wasted fuel out the exhaust, no mixing of exhaust and intake, just clean, efficient breathing. But wait, there's more. The V8 configuration wasn't chosen for prestige or to compete with Ford's marketing. Tahko realized that a V8's firing order could be used to create pressure pulses that aided cylinder scavenging. When cylinder 1 fired, its exhaust pulse would create a depression in the exhaust manifold just as cylinder 4 was beginning its intake phase. Each cylinder helped its neighbor breathe. The engine became a synchronized breathing machine where every explosion improved the next cylinder's efficiency. The intake port design itself was revolutionary. Rather than simple holes in the cylinder wall, Tahko created what he called directional velocity ports. Each port was actually a carefully shaped passage cast into the block, angled at 37 degrees, to create a swirling motion as air entered. This swirl continued through compression, improving fuel mixing and combustion speed. The ports were 18 millimeters wide, but only 8 millimeters tall, a radical aspect ratio that increased air velocity while minimizing the time they remained open. Cast passages in the block directed airflow from a pressurized chamber Tahko called the accumulator box, essentially a primitive supercharger driven by crankcase pressure. Now here's the kicker. The crankcase wasn't used for fuel-air mixture, like a traditional two-stroke. Tahko developed a dry sump lubrication system where oil was contained in a separate reservoir and pumped through the engine like a four-stroke. No oil in the fuel, no blue smoke, no fouled plugs. The crankcase only pumped air, which was mixed with fuel just before entering the cylinder through a primitive but effective mechanical injection system. Each cylinder had its own tiny fuel pump driven by a cam on the exhaust valve shaft, delivering precisely 0.3 cubic centimeters of fuel per revolution at full throttle. The engineering challenge of making this work was staggering. Every component had to be precisely timed. The exhaust valves were operated by a single camshaft running through the valley of the V, driven at crankshaft speed instead of the half speed of a four-stroke. The cam lobes were asymmetric, opening quickly but closing gradually to prevent valve bounce at high RPM. The followers were hollow, filled with oil that transferred through tiny passages to lubricate the valve stems. It was complex, but every complexity served a purpose. The cylinder head design deserves special attention. Cast from aluminum alloy, when most engines still used cast iron, each head weighed just 4.2 kilograms, complete with valves. The combustion chambers were hemispherical, providing ideal flame propagation, with the spark plug centered and the single exhaust valve offset to one side. The compression ratio was 7.8.1, high for the era, especially considering Finland's generally poor fuel quality, but Tahko's efficient combustion allowed it to run on 72-octane fuel without detonation. Let me put that in perspective. Ford's flathead V8, pride of American engineering, needed 70-octane fuel minimum and only ran a 6.3.1 compression ratio. Despite lower compression, it was less efficient. The flathead's combustion chamber design, with valves in the block beside the cylinder, created a long, tortuous path for flames to travel. Hot spots formed. Detonation was always a threat. Tahko's hemispherical chambers with central ignition achieved complete combustion in half the time. The bottom end of Tahko's engine was equally innovative. The crankshaft was a one-piece forging, not the three-piece design Ford used for cost savings. It weighed 11 kilograms and was balanced to perfection on equipment Tahko built himself, a spinning fixture powered by the mill's overhead shafts with adjustable weights to detect imbalance. The main bearings were pressure-fed through rifle-drilled passages in the crank, with oil flow rate controlled by the pump speed. At 4,000 RPM, the engine circulated 12 liters of oil per minute, exceptional for 1932. The connecting rods tell their own story of innovative thinking. Rather than the typical I-beam or H-beam sections, Tahko used tubular rods made from chrome molybdenum steel. They were lighter than conventional rods, but equally strong, gun-drilled for oil passages that lubricated both the wrist pin and cylinder wall through tiny jets. Each rod weighed 385 grams. Ford's weighed 580 grams. That weight reduction meant less reciprocating mass, allowing higher RPM and smoother operation. Power output was remarkable for the displacement. At 4,200 RPM, the engine produced 120 horsepower from 3.3 liters. That's 36 horsepower per liter, extraordinary for 1932. Ford's 3.6-liter flathead managed just 18 horsepower per liter. The torque curve was even more impressive. Peak torque of 180 pound-feet arrived at just 2,100 RPM and stayed nearly flat until 3,500 RPM. This broad torque band made the engine exceptionally flexible in real-world driving. But numbers only tell part of the story. Tahko needed to prove his engine could survive the torture of actual use. Finland's roads in 1932 were mostly gravel or dirt, with grades that would challenge modern vehicles. Winter temperatures dropped below -30 Celsius. Summer dust storms could clog an air filter in minutes. If the engine could survive Finland, it could survive anywhere. The test vehicle was built on a modified DKW chassis, chosen because DKW already used two-stroke engines, and the Finnish automotive community wouldn't immediately dismiss it as heretical. The chassis was lengthened by 300 millimeters to accommodate the V8, with custom motor mounts fabricated from steel plate. The total vehicle weight was just 9 to 80 kilograms, remarkably light for a V8-powered car of the era. For comparison, a Ford Model 18 with the flathead V8 weighed 1,315 kilograms. Initial testing revealed problems nobody had anticipated. The engine's power pulses, occurring twice as often as a four-stroke, created harmonic vibrations that cracked the exhaust manifold after just 200 kilometers. Tahko redesigned the manifold with flexible joints between cylinder pairs, allowing thermal expansion and absorbing vibrations. The intake system also needed revision. The original accumulator box created standing waves at certain RPMs, disrupting cylinder filling. Adding internal baffles and changing the box volume solved the resonance issues. The most serious challenge was cooling. The engine produced more power per liter than anything else on the road, meaning more heat to dissipate. The original radiator, sized for a four-cylinder engine, couldn't cope. Summer testing saw coolant temperatures reach 115 degrees Celsius. Tahko designed a new cross-flow radiator with twice the surface area and added an engine-driven fan with thermostatic control, advanced features for 1932. He also modified the cylinder head cooling passages, creating directed flow that eliminated hot spots around the exhaust valves. By autumn of 1932, the engine was ready for public demonstration. The Scandinavian Hill Climb Championship provided the perfect venue. These events weren't just about power. They tested durability, flexibility, and driver confidence. Courses included everything from smooth tarmac to loose gravel, with grades exceeding 20%. Engines had to pull from low RPM, accelerate smoothly, and survive the abuse of competition. The first event was in Turku, Finland. Tahko's car was entered in the unlimited displacement class, competing against Mercedes-Benz SSKs, Bugatti Type 35s, and modified American V8s. The Mercedes had 7 liters and supercharging. The Bugatti had 8 cylinders and decades of racing development. Tahko had his experimental engine and the skepticism of everyone present. The result shocked everyone. Tahko's car completed the 4.2-kilometer course in 3 minutes and 47 seconds, beating the Mercedes by 8 seconds and the Bugatti by 12. But it wasn't just the time that impressed observers. The engine's flexibility was unprecedented. While competitors downshifted for every corner, Tahko's broad torque band allowed him to stay in third gear for most of the course. The exhaust note was unlike anything they'd heard. A sharp, aggressive bark that occurred at twice the frequency of a four-stroke V8. Word spread quickly through Scandinavian motorsport circles. At the Swedish Grand Winter Rally, Tahko's engine faced its toughest test yet. 400 kilometers of ice-covered roads and temperatures reaching -25°C. Four-stroke engines struggled with carburetor icing and oil thickening. Tahko's mechanical injection and pressure lubrication proved superior in extreme cold. He finished second overall, beaten only by a factory-backed Mercedes team with 3 times his budget. Let that sink in for a moment. A self-funded Finnish engineer with a converted warehouse and 2 assistants had created an engine that could compete with the best Germany and France had to offer. And he did it with a design principle everyone else had abandoned as hopeless. The fuel economy achieved was perhaps even more impressive than the performance. During a measured test from Helsinki to Tampere, 180 kilometers of mixed driving, the car averaged 9.4 liters per 100 kilometers. That's 25 miles per gallon in American terms. Ford's flathead V8 averaged 15-17 mpg in similar conditions. The two-stroke, despite firing twice as often, was more efficient. How? Complete combustion, minimal pumping losses, and no energy wasted on unnecessary valve operation. Tahko documented everything meticulously. His notebooks, preserved in the Finnish Technical Museum, contain over 2,000 pages of calculations, sketches, and test results. He recorded exhaust gas temperatures at various loads, measured bearing clearances after every race, and analyzed oil samples for metal particles. This wasn't just inventive genius, it was systematic engineering at its finest. The exhaust valve system underwent continuous refinement. The original solid valves were replaced with sodium-filled hollow stems for better heat dissipation. Valve seats were induction hardened to depths of 2 millimeters, then ground to mirror finishes. The valve springs were wound from Swedish steel with progressive rates, softer at low, lift for quiet operation, stiffer at high lift to prevent float. By 1934, the valve train could survive 5,000 RPM continuously, remarkable for the era's metallurgy. One innovation that deserves special recognition was Tahko's approach to mixture preparation. The mechanical injection system used tiny plunger pumps, but the fuel wasn't simply squirted into the airstream. Each injector included what Tahko called a distribution disc, a spinning element driven by exhaust valve motion that atomized fuel into droplets averaging 50 microns. This fine atomization, combined with the swirling air motion, created near homogeneous mixture. Combustion analysis showed less than 2% variation in temperature across the chamber. The ignition system was equally advanced. Rather than a single coil and distributor like conventional engines, Tahko used 4 coils, each serving 2 cylinders. The coils fired waste sparks, one cylinder on compression, its paired cylinder on exhaust. This meant no distributor, no rotor, no mechanical wear items in the ignition. Spark timing was controlled by a centrifugal advance mechanism accurate to within 1 degree. The spark plugs themselves were custom-made with extended electrodes that projected into the combustion chamber, ensuring reliable ignition of the swirling mixture. By 1935, Tahko had built 3 complete engines with various improvements. The third iteration produced 135 horsepower at 4,500 RPM, a 12.5% increase through refinement alone. Bore was increased to 77 millimeters, stroke kept at 72 millimeters for a total displacement of 213 cubic inches. The combustion chambers were redesigned with slightly reduced volume, raising compression to 8.2.1. The exhaust valves grew from 32 to 34 millimeters diameter, improving breathing at high RPM. The automotive establishment's reaction was mixed. Finnish engineers admired Tahko's innovation but questioned the commercial viability. Swedish manufacturers showed interest but worried about production complexity. German firms, particularly DKW and Auto Union, sent delegations to study the engine. They were impressed, but ultimately decided their existing two-stroke designs were adequate for their market position. The real resistance came from America. Ford's European division obtained detailed information about Tahko's engine through their Swedish dealer network. Internal memos, discovered decades later in Ford archives, show that engineers in Dearborn took the design seriously enough to build their own test version. But Henry Ford himself reportedly killed the project, stating that the public associates two-strokes with motorcycles and outboards, not proper automobiles. Marketing perception trumped engineering merit. Think about that for a second. Ford spent considerable money investigating and even prototyping Tahko's design. Their own engineers confirmed its advantages, but they abandoned it because of public perception. This wasn't engineering. Conservatism. It was marketing cowardice. General Motors showed more vision. Their German subsidiary, Opel, invited Tahko to Rüsselsheim in 1936 to demonstrate his engine. The test was comprehensive. Dyno runs, durability testing, even a prototype installation in an Opel Admiral chassis. GM's engineers were particularly intrigued by the power density. An internal report stated, "Herr Tahko's design achieves power-to-weight ratios we cannot match with conventional four-stroke architecture. The complexity concerns are overstated. Proper manufacturing would simplify production considerably." But world events intervened. By 1937, European manufacturers were increasingly focused on military contracts. Two-stroke engine development shifted toward aircraft and tank applications. Tahko received offers from both Finnish and Soviet military contractors, but he refused weapons work on principle. This decision, admirable as it was, effectively ended his automotive engine development. The last racing appearance of Tahko's V8 was at the 1938 Midnight Sun Rally in northern Sweden. By then, the engine had been refined to produce 140 horsepower with remarkable reliability. It completed the grueling 1,200-kilometer event without mechanical issues, finishing fourth overall against full factory teams. The winner, driving a BMW 328, later wrote, "The Finnish car was always pressing. In the forests, where flexibility mattered more than peak power, it was often faster than my BMW. Only on long straights could I pull away." What makes this story particularly frustrating is how close Tahko came to revolutionizing automotive engineering. His patents, filed in 12 countries between 1932 and 1938, described innovations that wouldn't appear in production engines for decades. Variable valve timing through pneumatic actuation, stratified charge combustion using dual fuel injection, even primitive electronic engine management using vacuum tube circuits. He was thinking 30 years ahead while working with 1930s technology. The influence of Tahko's work extended far beyond his lifetime. After World War II, his designs influenced the development of two-stroke diesel engines for marine and stationary applications. The Finnish company Wärtsilä, now a global leader in ship engines, hired two of Tahko's former assistants who brought his principles to their diesel development. The idea of using exhaust valves with intake ports became standard in large two-stroke diesels, though few know it originated in a Helsinki warehouse in 1932. Let's talk about what might have been. If Tahko's design had been adopted by a major manufacturer, the entire trajectory of automotive development could have changed. Imagine cars with engines 40% lighter but equally powerful, better weight distribution, superior fuel economy, lower manufacturing costs once production was optimized. The American muscle car era might have featured high-revving two-stroke V8s instead of massive, big blocks. The oil crisis of the 1970s might have been less devastating with inherently more efficient engines. The technical legacy is undeniable. Modern engineers studying Tahko's notebooks find ideas still relevant today. His work on mixture motion predated modern computational fluid dynamics by 50 years, but reached similar conclusions through careful experimentation. His valve cooling strategies appear in modern racing engines. His pressure wave tuning concepts are fundamental to modern two-stroke design. Even his failed experiments provide valuable insights. He documented what didn't work as carefully as what did. "The engine sang today," he wrote after achieving 140 horsepower. "All harmonics in agreement, all temperatures stable. This is what we worked for." Another entry after a valve failure during testing. "Metal fatigue teaches harsh lessons. Every failure brings understanding. We will make it stronger." His final automotive engine project, begun in 1939, was truly visionary. Using his two-stroke V8 as a base, he was developing a compound-charged version with both mechanical supercharging and exhaust-driven turbocharging. Preliminary calculations suggested 200 horsepower from 213 cubic inches, nearly 1 horsepower per cubic inch in 1939. The project was abandoned when Finland entered the Winter War against Soviet invasion. Tahko spent the war years designing generators and water pumps for military hospitals. After the war, Tahko continued engineering work but never returned to automotive engines. He designed industrial compressors, pioneered heat recovery systems, and consulted for Finnish manufacturers. He died in 1967, largely forgotten outside engineering circles. His engines survive in museums, still capable of running, testament to his craftsmanship. Visitors often assume they're seeing some exotic racing engine from a major manufacturer. When told it was built by one man in a converted warehouse, they struggle to believe it. The broader lesson here transcends automotive history. Innovation doesn't always come from established leaders with unlimited resources. Sometimes it comes from outsiders willing to challenge fundamental assumptions. Tahko didn't accept that two-strokes were inherently crude. He didn't accept that complex problems required complex solutions. He looked at established practice, identified its actual versus assumed limitations, and engineered around them. Modern automotive engineering could learn from Tahko's approach. Today's engines are marvels of technology, but also complexity. Variable valve timing, direct injection, turbocharging, hybrid systems. We've added layer upon layer of complexity to extract more from the basic four-stroke cycle. Maybe, like Tahko, we should be questioning the fundamental assumptions rather than just refining existing solutions. The story also highlights how non-technical factors often determine technical decisions. Ford rejected Tahko's design not because it didn't work, but because they feared market perception. How many innovations have we missed because companies prioritized marketing over engineering? How many Tahkos have been ignored because their ideas didn't fit established paradigms? There's something deeply inspiring about an engineer working in a freezing warehouse, out-innovating the largest car company in the world. It reminds us that creativity and determination can overcome resource limitations, that questioning accepted wisdom is not just acceptable, but necessary for progress. That one person with a vision can challenge an entire industry's assumptions. Today, as we transition from internal combustion to electric propulsion, Tahko's story feels especially relevant. The established automotive industry is scrambling to adapt, much like they dismissed two-strokes in the 1930s. Innovation is again coming from outsiders. Tesla, Rivian, Lucid. Engineers are questioning fundamental assumptions about what cars should be and how they should be built. The parallels are striking. In the end, Kaarlo Tahko's two-stroke V8 stands as one of history's great what-ifs. It proved that dismissed technologies could be refined into superiority. It showed that innovation could come from unexpected places. It demonstrated that engineering excellence transcends resources and recognition. The engine that was supposed to be impossible became the engine that made everything else look primitive. Even if it never reached mass production, it achieved something perhaps more valuable. It proved that accepted limitations are often just unchallenged assumptions. So, what do you think about Tahko's revolutionary design? Have you ever encountered similar examples where outsider innovation challenged industry orthodoxy? Drop your thoughts in the comments below. If you enjoyed this deep dive into forgotten engineering brilliance, make sure to subscribe for more stories of automotive innovations that changed the game or died trying. Until next time, keep questioning what everyone else accepts as fact.